So this lesson is on navigation problems, which are just really a practical application of vector addition. So navigations are good examples of vector addition problems. So in navigation problems, the velocity of a ship or a vessel must be added to the velocity that the medium, added to the velocity of the medium that the vessel is riding in. So the medium is usually water or air. They're usually boats or airplanes. So I'll show you an example of what this means. So here's a video of an airplane landing in super strong crosswind, so we can see what happens with the airplane. So you can see it's tilted in this direction. So what's happening here is the wind is super strong from this direction. So what the airplane has to do is it has to fly into the wind to compensate. So if they didn't, they'd get blown off the runway there. So if we continue the video, they straighten out right at the last second so they can be straight, and it blows them a little bit that way. But now the wheels are on the ground, so they're okay. Yeah, so that's what pilots have to manage. They have to worry about the vector addition of the medium, the air, as well as what direction their plane is headed. So here's another video. This talks about rip current. So the airplane, the medium was air, but it also works with the medium of water. So this talks about rip currents. We don't really know too much about rip currents because we don't live near oceans, but if you grew up in Australia, in elementary you'd learn about rip currents because they're super dangerous.
Australia has some of the best beaches in the world, and everybody loves going to the beach. But there's something on the beach called rip currents. Rips are something that every Australian and every overseas tourist should know about because there's something that can get you into trouble. I'm Dr. Rob Brander from the University of New South Wales, and I'm a surf scientist and surf lifesaver. During the summer months in Australia, on average, somebody drowns in a rip every 2 or 3 days, and most of the thousands of rescues that happen on our beaches are related to rips. Remember that it only takes about a minute to drown, so it's very important to be able to spot rips on your own. Now, if you haven't noticed, I've been swimming between the flags, and that's where everybody should swim because the lifesavers and the lifeguards put the flags in the safest part of the beach away from the rips. And if you don't know what a rip is, if you swim between the flags, that takes a lot of the guesswork out of having to spot one. However, of the more than 11,000 beaches in Australia, only 3% are actually patrolled by surf lifesavers and lifeguards. And that means there's a lot of beaches and a lot of rips that you could easily get into trouble in. Well, what are rips? It's a really good question. And what we do is we throw purple dye, which is harmless, into the water. The dye goes wherever the water goes, and it's an easy way to spot the rip. Well, let me tell you what rips are not. They're not undertow. They won't pull you under because there's no such thing as an undertow. They're not rip tides because they're not a tide. They're a current. They flow pretty steady, and they won't take you to New Zealand. Basically, rips are strong, narrow currents that flow from the shoreline through the surf zone and offshore. They exist to take all the breaking water that's piling up on the beach back out to sea. Here you see a nice green gap, almost like a road going through the surf. And that's the rip current because it's sitting in a deeper channel, in this case between the reef and the sandbar. But look at it, there's no waves breaking, there's hardly any white water. Whereas you look to the right, you've got your sandbar, shallow water, waves are breaking there, bringing all that water in and back out through the rip. It looks perfect, and that's how you spot it. It's a pretty scary experience getting stuck in a rip, and there's definitely some do's and don'ts about how you should behave if you do find yourself caught in one. The main thing is not to panic. Don't panic because the rip will not pull you under the water. All the rip will do will take you further out to sea, and it'll sometimes bring you back. Remember that you've got air in your lungs, you float, you're very buoyant, so don't panic. The second thing to do is if you're not a particularly good swimmer, put your hand up, straight up like that, signals for the lifeguards and the lifesavers to come and get you. What you could also do if you're a good swimmer is you could look around. And if you can see the sides of the rip, which is usually the shallower water where the waves are breaking, a lot of white water, swim towards that area. White water is good because it means it's shallow, you can maybe stand up, and also white water brings you back to the beach. What you should never do is swim against the rip. These things flow pretty fast, and you'll just find yourselves going backwards, swimming faster, getting tired, and then you'll start to get scared. So just go with the flow, signal for the lifeguard, or let the rip take you around and get out of it yourself. One of the reasons that rips are dangerous is that they flow faster than people can swim, and sometimes they can flow faster than even Olympic swimmers. Rips are most dangerous because they actually look like the safest place to swim. A view from a headland is always a good way to spot a rip because you're up high and you're looking down at the beach and they're a lot easier to see. And often surfers and swimmers will check out the beach for rips before they go down in the water. Not all rips are the same. The most common type is what we call a fixed rip. And fixed rips are stuck between sandbars and they might stay in the same place for days, weeks, and even months. Well, we've just had an example of a flash rip where all of a sudden the rip is pulsed out. Where those surfers are, you can see the chopped up, messy white water that's just gone out, and then it's just stopped. And that's one common thing about these flash rips is that they can suddenly occur anywhere where there's suddenly been a large group of waves breaking, and it pushes the rip out, and then it disappears. Finally, we get something called a permanent rip, or a headland rip. And these are rips that are pushed against the headland, and they're there almost all the time. So it's another good reason to always be careful when you're swimming close to headlands and rocks. If there's no lifeguards or flags on the beach, the simple rule is don't go in. If you do go in, make sure you're an experienced swimmer or surfer, make sure you're always with somebody, and make sure you know how to spot rips.
So here's an example that talks about the rip currents. So the average person is capable of swimming 1.5 meters per second. The rip currents are able to move at speeds up to 2.5 meters per second. So if a person is trying to swim east to shore, what is their true velocity if the rip current is headed east? So this wouldn't really be a rip current because it's sort of bringing you to shore. And this can happen as well. This is what waves do. So the person is swimming east. So this is the velocity of the person. And the velocity of the person is 1.5. And the rip current is also going 2.5. So this is the velocity of the rip. Well, if we do vector addition for this is just in one dimension. We've done this before. So the true velocity of the person is it's going to be adding those two together. So that's going to be 4 meters per second east. This is a true rip. So if the person is trying to swim back to shore, so that's 1.5 meters per second, and that's the velocity of the person, but the rip, which is stronger, is going 2.5 meters per second out that way. Well, we can say that this is positive and this is negative because they're going in opposite directions. So what we'd end up getting is we'd end up getting -1 meters per second, and everything going west is negative. So that would bring you out to the ocean. So that's all 1D stuff. So what we're focused on in this unit is we're focused on 2D stuff. So how would we add them together if, they're going in two different directions? So just erase that. So if the person's still trying to swim east to shore, so this is 1.5 meters per second, and the rip is going north at 2.5 meters per second, well, what's going to happen is the person is going to go this way, right? They're going to go a little bit angled. So if we want to find out their true velocity, well, we just have to Pythagoras that. So to Pythagoras that, we go 1.5 squared plus 2.5 squared. We square root our answer, and we get 2.9, right? So 2.9 meters per second. And we also need an angle, so this is opposite and adjacent, so we can tan -1 that of opposite over adjacent, and we end up getting 59 degrees, sorry about that, and this is northeast, so we're not going directly east, we're going north of east. So 59 degrees north of east. And if they're going south, well, that's the same thing, just in the opposite direction, right? These are going to be our two vectors, so this is 1.5, This is 2.5. This is our resultant. Well, we're still going to get 2.9 meters per second, but when we have this angle here, opposite over adjacent, it's still 2.5 over 1.5, we're still going to get 59 degrees, but what we're going to get is northeast, south. So I'm not going directly east, I'm going south of east. So we add them different when they're 2D vectors compared to when they're 1D vectors, and it's really important that you know that, and you don't ever try to add these ones together by just going 2.5 and 1.5. So when doing these 2D questions, when doing these navigation problems, an important question to ask yourself is to compensate or not to compensate. So when traveling in a moving medium, you can either compensate or not compensate. If you want to go straight across, you must compensate an angle into the medium. So this situation is what the airplane did. So you can see this is our vessel, this could be our airplane, and what we have is that the airplane heads into the wind. So the wind is going this way, and the airplane heads into the wind. And when we do our tip to tail, so this is the direction of the airplane, this is the direction of the wind, and this dotted line is always our resultant or our true velocity. And you can see that it brings them straight across. So lots of times this term will come up, still airspeed, or still water speed if it's a boat. So the still airspeed is how fast you would be going if there was no wind at all. So if you just headed in this direction, there was no wind at all, you would just go in this direction. But because there's wind blowing you this way, you end up going straight across like that. So that's if we are compensating. So sometimes with questions, you don't want to compensate. So if you don't compensate, you will travel straight across and you're just going to end downstream. So this is the direction of the boat. The boat goes straight across. The river moves them downstream. So because the river is pushing them downstream, this is the velocity that they go. And we'll do some questions that show each of these. Okay, so a plane is scheduled to fly at a velocity of 300 kilometers an hour straight south from Edmonton to Calgary. There's a crosswind of 50 kilometers an hour from the west, so in other words, headed east. So wind is always given from the direction it comes from. So it always say from the west, from the east, from the north, anything like that. So it's headed east. What is the direction of the plane's heading? And it's still airspeed. Okay, so that's what this still airspeed. So let's draw out a picture of what this would look like. Okay, so the plane is flying from Edmonton to Calgary, straight south Edmonton to Calgary. So there's a crosswind from the west, so the wind is blowing this way. And I always like to draw on the wind before I draw my tip to tail. So it's really important that this is my plane right here. You think to yourself, well, if the wind is blowing this way, what direction do I have to head my plane? Well, I have to go into the wind like this video that we saw. So this is the direction my plane goes. This is my still airspeed. So if the air is not moving, this is how I'm going. Okay, the wind is going to blow you this way. So my resultant, this is our resultant or true velocity, is going to be that way. So this is our tip to tail vector diagram. So we can fill in some stuff. So it says that the wind is 50 kilometers per hour. It says that the plane is scheduled to fly at a velocity of 300 kilometers. So the plane is supposed to fly 300 kilometers an hour that way. So it's asking for our still airspeed. So we need to find this, which is our hypotenuse. So we have to go 50 kilometers per hour squared plus 300 kilometers per hour squared and square root it. And we can find our speed. And then to find our angle, we're going to tan -1 opposite over adjacent. So 50 over 300. So we'll do both of those in our calculator. So it's going to be 50 squared plus 300 squared. And we're going to square root our answer. So we'll end up getting 304 as our airspeed, which makes sense. If you're flying into the wind, you're going to fly a little bit faster. And then we can tan -1 our 50 over 300. And we end up getting 9.5 degrees. And our 9.5 degrees, if I draw on north, east, southwest, I'm not going directly south, I'm going west of south. So that would be my answer. So another type of question that we can see, ferry heads across a channel at 10 kilometers an hour, headed due west. There's a cross current headed due south at 2 kilometers an hour. If the channel is 5 kilometers wide from east to west, how long does it take the ferry to travel across? Okay, so we got to draw a picture because this is quite confusing without a picture. So a ferry is headed across the channel headed due west. So this is the heading of the ferry. So that must mean that my channel, my river, is like that. Okay. There's a cross current headed due south. So this is the current of my river is going that way. And it says that the channel is 5 kilometers wide. How long does it take the ferry to cross the river? So if my ferry is headed due west and my river is headed due south, it sounds like that my ferry pilot is not compensating. So it sounds like the river is going to move it that way, going to push it that way. So this is my resultant. So this would be an example of something that's not compensating. So we can fill in some numbers here. So it says that the speed of my ferry this way is 10 kilometers per hour. My distance this way is 5 kilometers. And it says that there's a, oops, give myself a little bit more room. The speed of the current is 2 kilometers per hour. And that's all that we know, okay? So what we need is we want to find out how long does it take the ferry to cross the channel. So we want to know time. So this is a common question where we want to find time. And if we think, so let me ask you a question here. So if the ferry, let's say the ferry went across the channel at 10 kilometers per hour and 5 kilometers for the distance. And at this exact same time, a ferry went across, it blew it down like that, or pushed it down like that, and the ferry went this way. So the time it takes to do this, where the ferry's moving in the moving river, taking this distance, and the time it takes to do this, which one do you think is going to be quicker, going straight across or going the hypotenuse? So a lot of people will say this will be quicker because, well, it's a shorter distance, right? And a lot of people will say, well, this is going to be quicker because you're going faster. But you're both kind of correct. This is a shorter distance, this is faster, so the time actually ends up being the same. So if we find the time that it just takes to go straight across, it's going to be the same as the time it takes to go here. And it's going to be the same for the time that it takes to get pushed down river. So the time is the same in every single part of our triangle. So if we just find the time in one of the triangles, then we're good. And we can use v equals d over t, t equals d over v. If we just use this, our distance is 5 kilometers straight across. We're going 10 kilometers per hour. 5 over 10 is half an hour, or 30 minutes. So that's our answer. So we don't actually need to find the time for the path that it actually goes, because it's going to be the same for the time if it was moving in a river that wasn't moving at all. So let's finish off this lesson with a board question. So a river flows south. A riverboat pilot gives the boat a heading of 17 degrees north of west and is able to travel straight across the river at 6 meters per second relative to the shore. Determine the speed of the current. So pause the video, try it on your own, see if you can do it, and I'll go through it right now. So it sounds to me like this riverboat pilot is compensating. Okay, so the river flows south, right? So that means that our river looks like this. A riverboat pilot gives a heading 17 degrees north of west. So north, east, southwest. So 17 degrees north of west would look like that. So this is the heading that the riverboat pilot takes. It says that the riverboat pilot travels straight across, and that's because the speed of the current pushes it downwards. So this is 17 degrees right here. So we've built our triangle, and it says that the riverboat pilot is able to travel straight across the river at 6 meters per second. So this is my 6 meters per second. So the riverboat pilot must go a little bit faster. But we want to determine the speed of the current. Well, we have a right angle triangle, we have a side and we have an angle, so we can just use SOHCAHTOA. We have opposite and adjacent. So we set it up, tan theta equals opposite over adjacent. We want to find opposite, so we just move adjacent up there. Well, that's really easy. We just go 6 meters per second, tan of 17 degrees. So if I go 6 tan 17, 6 tan 17, then I end up getting the speed of the river, which is 1.83 meters per second. Okay, south. So, but it just asks for speed, so direction doesn't matter. Oops. Okay, this is your homework. So just 4 navigation problems, so not a ton of homework. So give those a go, and let me know if you have any troubles.